Welcome back for today's session called as Distribution Approaches and Word Embeddings in NLP. In the earlier sessions till now, we have seen and discussed about what are the applications of NLP and introduction part to NLP, what are the core tasks of NLP. Next, what are the language basics starting from pragmatics to morphemes and leafemes. Next, we have seen the language basics, approaches to NLP. Next, what are the basic pre-processing steps and NLP pipeline. All these things we have covered in the earlier sessions. Now, we'll be moving forward to the text distribution techniques and word embeddings. We have covered the basic vectorization approaches like TF, IDF, count vectorizer. Yes. Next, bag of words, bag of n-grams, all these in the earlier sessions. Today, we will be discussing about how these words are being distributed across the vector space and being mapped or grouped into the similar clusters. That we have the techniques as the basic techniques as word-to-vec, GLOVI, fastest and word embeddings. First of all, what do you mean by word distributions? So in the vector space model, if you consider the examples like the jump or jumped, sing or singing, yes, love, like, adore, all these terms which are similar and have some similar semantic meaning are grouped into some common vector format so that we can perform some mathematical operations even for these assigned or obtained vectors. We could see that we have the man and the woman or the human species all belonging to one category. If we have a gender and all, then we have the king and queen. If we could do some mathematical operations like king minus men and all, then it would result into women. I can perform some mathematical operations for the queen and then I may result in some other thing. So if you could see, all these are the names of the countries. Here you have all the names belonging to Germany, but all into some category. So this is based on the gender, this is based on the capital, and this is based on the tense form, where we have the present tense and we have the past tense. Maybe here we swim and swam, jump and jumped and all. So word embeddings or the dynamical or the distributed word representations are where we are trying to group them all the words with similar meaning at some common representation form. In count vectorization techniques, bag of words and all, we are representing all the words and all into numerical form, either one-hot encoding or the count vectorizer or the bag of words in the form of zeros or ones. And there is some limitation that we are not able to try the semantic or the significance of that. Maybe in TF, IDF and all, we are giving some priority or some significant weightage to the important terms that are being occurred in the existing raw corpus or the raw input text, but still we require some more sophisticated and more pre-trained kind of the embedding technique or making all the common words to stay at some common place or the platform. For that, we have these popular word embedding techniques as word-to-vec, GLOVI, fast text, and word embeddings, which is being developed by the Google and all. Nowadays, in order to perform the basic dynamical and all the NLP operations, people have moved to usage of word embeddings. First, coming to the word-to-vec. So, in the word-to-vec, as a name itself, it is where we are representing the vectorization form for the particular word. So words are being converted in the form of the vectors. Hence the name we have word-to-vec. So what does this word-to-vec you have? Basically, two types of techniques called as CBO. When we are making those vectors from the available words, suppose I have the vector, I have the available terms as love, I have like, I have hate, I have liking, fine, famous, adore. All these I have. So for all these words, I'm going to represent in the vector form by using continuous bag of words as well as skip gram. Now in this session, we will be discussing how the continuous bag of words and the skip gram model will help us to model the embeddings and all. So and also one more advantage with moving to this embeddings and all is that they use the less space when compared to word encoding, because in one hot encoding or the count, the simple vectorization techniques, maybe it works for small data set or a small corpus which is having a row or a column of 100 to 100 or 1000 to 1000. But when you have a huge kind of the density and all, our vectorization, our mathematical calculation may become very clumsy and all. So in this, all the similar terms are being mapped into small dense embeddings vectors, and then they are again layer by layer by the use of neural networks, they are again being mapped and maintaining with some semantic representation. So we could see in this word to vec, I have some sentence called as I love NLP, and also I have I adore NLP. So if we could see the semantic similarity between the love and adore, we could see the similar terms which are similar to love. In this example, I and I are same natural language processing and all and same, but the similarity between the love and the adore term, we could see that it is the word similar to adore is 0.24, whereas the others are 0.09. Here it is the vector representation or the similarity, the similar vector for the word love is here, it is minus 0.5, next minus 2.7 and so on. So we could observe that, we could conclude that this is having the more matching similar vector, which is an adore matching with the word love. Yes, so likewise, it is easy for us to make use of these word embeddings, word vectors and all to decide and to see what are the matching terms for our available terms. Now, coming to the continuous bag of words, as the name itself, it tries to analyze, its main objective is to try to predict the target word from the available neighboring terms. I repeat the point, the main objective of continuous bag of words is to predict a target word based upon its context. So I have a context now, I call it as I love NLP and all. I have the term context, I am discussing about NLP, I am discussing about natural language processing, the techniques, about talking the embeddings, about text representation, about feature modeling and all. Then obviously it is now revealing some outcome or some target term talking about the word called as NLP. So given a sequence of words, given a series of the words, neighboring words, then its objective, the continuous bag of words objective is to predict the target word. Now, this is how it is being illustrated, and it's a feed-forward neural network. So we could see this example here. NASA launched dash last month, and I have some probable neighboring nodes as table, you have angry, you have truck, you have rocket, apple, pizza. So now the objective of this CBOW is to determine the target word which is most matching from the available terms. From the available, maybe table, maybe angry, truck and all are having less probability which is matching to this. So NASA, when I'm talking, it tries to determine where the nearby words have been used in and around with NASA, in and around with launch and so on. So you have the rocket as a target outcome from the given neighboring terms as table, agree and all to predict that NASA launched rocket last month. This is how the neural network arrangement is also there for CBOW and skipgram. In this, you have the input terms. Next, based on this neighboring nodes and all, you are determining the target. Whereas in the skipgram, its the policy is to skip and also you will determine the context words, the neighboring and all given from the target. So if I have the target, if I say my target term is rocket, then it will determine the neighboring words as truck, apple and all, or near terms which is near to the rocket term. One more example we could see in the skipgram. As I have specified, in the skipgram, our main task is to predict the center word from the given in neighboring nodes and all. Yes, so this technique is specifically helps us to determine or to deal with less frequent terms and all. Maybe in the above example, apple and all, maybe they may have apple and all in the NASA and all, but angry, table, truck and all are not non-suitable terms, are less frequent terms which are associated with the term called as target term we have here as rocket. So likewise, it is easy for us to analyze. So continuous bag of words and skipgram are good word embedding techniques that go into the word to vec. So I have one more example which is taken from the standard textbook. The quick brown fox jumped over the lazy dog. Now I have in the skipgram, I am going to determine this context, this main center word where you have from the brown fox, you have the input as jumped. Now I have to assess that brown. How was the fox? It was brown in color and it jumped over the truck or over the lazy dog. This is how. So in the skipgram, your projection is the skipgram given the center word. Now I have been given with the input as jumped. Now I have to determine the neighboring words or the neighboring context words in and around with jumped. Given I have a window size of 3 or 5 and so on. So overall, we could see that the same example, quick brown fox jumped over the lazy dog. I have that in context bag of words. I have been given with this available terms. I have a set as brown. I have a set as fox. Next I have over. Next I have the some under and so on. Then I have to determine my given the context words and all, then I have to determine this center word. Here my center word, this is my target word. Whereas in the skipgram, it is in the reverse. In the skipgram, given the center word, I have to predict the neighboring or the in and around words which are available in the context. So actually what happens, I have also taken one more example called as students learn machine learning techniques. I have, if you could see the window size as 3. So what does this do? The processing and all is conceptually to determine for the word learn and all. So one word to the left and one word to the right. Yes, suppose I have students learn machine learning techniques. So one word on the left is, now I have the first word as students. In the context word bag of words, I should give the input as my context words. So I should give the set like this. Then it will predict the output as a context or the center word or the middle word, what we call. So I have students, one to the left and one to the right is I have machine. If I take learn as my target term. So one to the left is students, one to the right is machine. Similarly, if I take machine, then one to the left is learn, one to the right is learning. Similarly, if I take machine as my thing, then one to the left is learn, and I have told my, if I take learning as my thing, then one left is machine and one right is techniques. One is the machine and one is the tech. Then my target terms are the learn itself. Next here the machine. Next I have the learning. Yes, so this is how the strategy follows if we are considering a window size as 3 and then my simple sliding window portion is as considered as 1. Even you can also consider as 2, 3 and so on. In the skipgram, what happens is the same process. We have one word to the left and word to the right, but I have all my input terms like learn is one input term. Next, I have machine as one context term, learning as one, techniques as one. Then I have to predict the context, but that's the center word. This is how the strategy reverts in CBOW and the skipgram. We'll also come across in the BERT model, where in the BERT model it is trying to use the approach of masking strategy, and it also considers both the left as well as right, and also gives some contextual embedding, but gives some masking form of the thing. Then it may predict the most masking approach or the most occurred word for the learning techniques or machine learning or AI techniques, as people are more talking about AI and ML in the most of the sources. This also is a very good example. I have taken one more source. I am happy because I am learning. In this, I have a context word size of 2 and the window size as 5. This is 1, 2, 3, 4, 5. In the window size of 5, I have my context size as 2. I am is 2 because I. So to the left, to the right. So for each individual words as I, am, because, I, and all, you have to, maybe the one hot encoding individual vectors may be like this for all. Let's say am to am, because to because, happy to happy, and so on. This is my individual corpus for this. After identifying the vocabulary for the size of 5 and all, then I have for this set as am, because, happy. Likewise, you may also have all these context words, then you do some operations. I am is one combination, because I is different, am because is different, and similarly then divided, and we can finally get some final vector representation forms which are going to arrange in the sequence of. With these, I can have my all my training context words, and then I can determine the center word and then represent it in a word vector form. So this is how it happens in Word2Vec for the embeddings and all. Normally, what happens in all the traditional vectorization techniques is for I am having some representation, for am, for because, and so on. But here you are having some more weightage and all, where you are determining the target terms or as well as the context terms. Next is the GloVe. In the GloVe, you have global vectors for word representation. Global, as the name itself, it is an overall trying to reflect the overall meaning of the words. In the word to CBOW and skipgram, you are doing with the context words as well as with the availability of the center terms and all. But it is trying to provide the overall leveraging the word to word kind of the vector, global vector representation with the co-occurrence. Suppose in this example, I have a vector of winter, cold, snow, sports and all. In this, I have a vector for one word called as winter. I have a vector for one word called as cold. Similarly, a vector for snow. Similarly, a vector for sports, and so on. In this, we could see that you have the terms where the words are being represented in the vector form, and also you are seeing the co-occurrence along with winter, what terms have been occurred. So winter to winter it is 5,000, say. Here we have cold is 500. For snow it is maybe winter sports it is 2,100 and all. So if you could see an example, ice hockey is a winter sport. Yes, along with ice, you also have a hockey, which is a sport which is being talked about and which is being played in the winter season. So the winter sports, you have the vector, the count as 2,100. Similarly, for the winter, you are having with respect to winter 5,000. With respect to sports, you having, of course, here it is reflecting not anything on it. So this kind of co-occurrence representation, along with winter, what do you have? Along with cold, along with love, what do you have? Yes, am I talking about some costume, about some subject or some codes, or I'm talking about some eatable, what is the context, and all these being considered. And also it considers mathematically least squares regression technique to factorize those co-occurrence matrices. It's a good low dimensional space kind of representation. It's a very good approach. But it performs as an overall kind of a word represent. And for the famous example is this one, which is taken from the globe as Gigi word, which is having a 100 to 100 dimensional vectors for the available terms and all. It also, in this example, you could see for the global. So we are going to represent or going to import with the keyed vectors, and I have taken my word pairs as learn, learning, India, Indian, and so on. I have some pairs. If you could see in the globe wave, you could see that the similarity between the term learn and the learning is 0.8. Yes, whereas from India and Indian it is 0.86. Next, fame and famous, it is 0.58. We could see that you have a less significant, less similarity between these two terms. Means in this GLOVE and all, keypad and overall the word embedding and all, we could see that most of the people have not used the terms fame and famous simultaneously or synonymously. So you have the variance as 0.5. Maybe it may change in fastest, it may change in BERT, or it may change when we are going to do with the CBOW or the skipgram. The same example, we can also see what happens with the fastest and BERT model and all. Now comes the next word embedding technique. In short, is the fast text. As the name itself, it's a fast approach. It learns from subwords. In the CBOW, skipgram and all, we are doing with reference to the in and around neighboring words or the contest words. In GLOVE and all, we are overallly trying to relate and form a core occurrence matrix, whereas in fastest, it is trying to also learn from the subword. What or how the individual characters are being grouped up and all, or what we call engrams and all. So character engram. Suppose I have a word playing. So how it is being grouped up? Play as one thing, PL as one, AY as one, ING as one, AY as one. You could see here PL, PLA, next LA, next AY, IN, ING, next only NG, and so this is a complete vector for an engram representation for the word playing. Likewise, in the fastest, it is going to represent all the words and all in the form of bag of character engrams, where the character engrams may be 2, 3 and so on. Now, what happens, the main advantage with this fastest word representation is our misspellings or raw spellings or rate spellings may be overcome. Now also for Apple, if we could choose n equals to 2, AP as 1, PP as 1, next PLE, LE and so on. So it represents all the features and all in a space or a vector of a bag of n grams. So character by character it is going to take into consideration. So it is also called as word, a set of a bag of character of n grams. So in this spelling for playing and all, maybe the spelling PLI and all may be corrected or may also be handled. In this example, if we are for the same set learning, India and Indian and all, we could see that the similarity, if we could change in terms of fastest and all, now the similarity has changed. In the earlier it was 0.8 and all, if you could remember. Now it is 0.7 and all. Now it is of course the same thing for even for this also. But here this is how this is, I have included the subwords of 300. This is a good API which is a pre-trained fastest model. By importing this, then you can similarly try to define the similarity between the each individual terms, or also you can write some corpus of individual paragraph text and then validate it. Next comes about the BERT model, bidirectional encoder representation from transformers. The name itself, it tries to traverse to the left as well as to the right. That's why the name you have left, and it generates both bidirectional context-aware word representation by also following the predicting the masked tokens. Maybe I love to learn NLP, or I am learning machine learning and all. So the machine is the term which is being masked, or I have AI as I was discussed. Most of the people are talking nowadays about AI, about ML. So likewise, in this BERT model, it tries to determine that word by providing those masking and all, which is taken from the large corpus input data set or Toronto book corpus, which forms a large corpus, and from that it is trying to predict the next word prediction or the sentence word. Now for the same example, for the same pair, I have learning, India, Indian and all. We could see that in the BERT, the accuracy is here 0.9, whereas in the earlier it was 0.8 and all. from learn and learning means most of the people, when you are trying to assess with both left and right and all, you have 0.9. Whereas for India and Indian, it is zero point 0.9. Here it is has changed. Fame and famous, it is 0.9. When we are trying to use this bird case, of course, here uncased means which is away from the uppercase and font case and all. So this you can import it. You can import the same direct model and then we can tokenize it, make some cluster, make some document corpus name, and then by using the simple for loop, we can just simply trace out this embeddings and all. Even when we are trying to implement it for the neural network models and all, just by importing the epochs, the number of layers and all, we can just do it in detail to handle the real-time applications. But just now I have taken a small example by taking the pair of learn, learning, India and similar terms which are more or less same but may not be semantically or contextually may be different. So overall today, to summarize, we have discussed about word2vec, GloVe, fastest and bird embeddings, where word2vec tries to learn and represent the overall word vectors and predicting the context words, either in terms of target or in terms of the in and around terms. In GloVe, which is forming an overall global vector with the co-occurrence. It's good and also a good approach, and it performs in general of co-occurrence matrix with the types of linear regression logistic. Next is the fastest, where you have the representation of subword vectors and then where you are having the representation in terms of bag of n characters. Next is the bird embeddings, which is a good one, which is a good pre-trained model, and where we are learning the contextual vectors in a masking feature, and it is helpful generally for the large pre-trained data sets and all. If you could see the scenario or the flow from the context words to the co-occurrence matrix to subwords and all is the bidirectional transformers. People more often use this to handle their large applications or where they are in use of dynamical usage of the words and all the context have been changing from situation to situation. You also have an representation as universal language representation. So till now we have seen word or vectorization approaches. Yes. Next we have seen distributed representations. Next also we can also make overall language also to be represented. Sentence representation. We can also make manual representation. Yes. So in this we have an example. I love NLP. You can make the entire vector representation for the sentence itself with some fixed matrix and then you can make overall change for it. That we call it as universal language representation. Also we also call as universal sentence encoder. Not only the words are being embedded, we can also do some kind of encoding representation for the entire sentence. Suppose I have I enjoy NLP and I have already returned some kind of an encoding for this sentence as I love NLP. Now whenever I say I enjoy natural language processing, I can make some kind of an encoding representation for the word NLP wherever natural language processing has come. Maybe it can be tokenized with similar vector called as NLP. Yes, if I am talking about machine learning, artificial intelligence and all, maybe I can sensitize to AI, to ML and so on. So here in this example, I love NLP and I enjoy natural language processing may result as a similar vectors. Wrapping up for today's in short is till now we have seen the basic vectorization approaches, the distribution approaches, universal language representation. We also have handcrafted where you can use n-gram modeling, where you can use bag of words. Still we can use all this to design our own linguistic domain specific embeddings as well as some attributes. Thank you. Next, we'll be discussing about the classification techniques and also how to evaluate and all in the next session. We'll also come across some NLP data sets and all in the next sessions, where the students can use the titles on all the data sets for their projects and also for their assignments. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.